Now, specifically, I want to talk about identity. This just means proven patterns. There's some proven patterns. And I want you to know that I'm going to write down a bunch of different things, and I'm not actually solving any problems per se. I'm just going to think of this way. Math is like English. Math is a language, right? And sometimes when you're when you're in an English class, you're not necessarily writing a paragraph. You're just writing a random sentence, and then as long as that sentence makes sense, you can like kind of analyze that sentence. So what we're doing is I'm going to write these mathematical equations, and within this, we're trying to understand how they fit with each other, and they're not necessarily solving a particular problem. Because once we begin to understand how they relate to each other, then we can take the result of that, and then we can like take that as a tool and then solve real problems. Does that make sense? So right now, we're not solving problems. We'll just kind of look at a mathematical statement and say, do I understand how one side is equal to the other side? And is it logical or not logical? Can my brain go from right to left and then left to right again? Does that make sense? So in this case, some obvious one that you learned before, a plus b times a plus b, right? That's easy. A plus b squared, right? Equal sign, just the way you connect. What's the answer? Like what can it be? Right, a squared plus
a squared plus bx plus c.
Is it this?
Yeah. No, that's not correct.
Why not? Can this exponent just distribute into the parentheses?
I feel like no, it can't.
Like so, for example, 2 plus 3 squared is 5 squared, which is 25. But can this question mark be 2 squared plus 3 squared, which is 4 plus 9, which is 13?
No, it can't be.
No, right? So we can't do that.
A squared plus 2ab plus b squared.
Right. So you had to, right, do the FOIL, right?
Oh yeah.
When you do FOIL, right, is a squared plus ab, and then go to b now, plus ab, and now notice I still put a in front, right? Even though this is b first, b times a, ba, but ba is ab, right? So I just write ab. And then lastly, b times b is b squared, so we get a squared plus 2ab plus b squared. Right? Now, what is cool about this, right? I'm gonna erase this part just so that I have a nice list, is that I skip this one, I just keep this one over here. I'll just write this as a squared plus 2ab plus b squared. Now I know that this is indeed this. My brain can go back and forth between these three sections, so that next time when I have, say, for example, 2x plus y squared, and all of a sudden, I don't really need to worry about, multiplying out. I can simply use this and say, oh, my a is 2x, my b is y, then a, right, become 2x squared, right, 2 times 2x, times b, which is y, and then y squared. I end up with 4x squared plus 4xy plus y squared, right? So I take this pattern that I just in my head makes sense. This indeed is this. Then this becomes a tool that I can use to apply to a more complicated problems that you'll be asked on the test. Make sense? That's the application, right? This is how we apply this identity. This is what we call the identity or proven pattern. And we use the proven patterns and apply into the specific problems. Questions before I add more identities? In fact, I'm going to add 4 more. This is just one of them. Yeah, it's okay. You're smart enough to handle this. All right, next one. A minus B times A minus B equal to A minus B squared. If you do the multiplying out process, what would you get? Go ahead and write it on the side, but keep track of a list like this. See what you get. See what you get. And again, remember, these things are these. At the very least, you need to remember is you cannot distribute the exponent, right? Don't do that. Don't make that rookie mistake. All right, so if I FOIL now, see if you get this. I'm not going to show you the process, I'm going to show you the answer or the result. You end up with a squared minus 2ab plus b squared. Okay? So the only difference, right? The only difference is just this one right here. Instead of plus, you get a minus. But hey, all these other terms are exactly the same, except the 2ab. Instead of plus 2ab, you end up with negative 2ab. Okay? So that's identity number 1, identity number 2. Now in this one, give you another one, a plus b times a minus b. All right, multiply out and see what you got. Okay, let me show you over here. So a plus b, a minus b, okay? Let's do FOIL. So a squared minus ab. So far so good. B times a, which is plus ab. And then b times negative b is minus b squared. Minus b squared. So now you got negative ab plus ab. They go away. You are left with a squared and then the negative b squared. So that's the answer. A squared minus b squared. A squared minus b squared. Okay, so I'm gonna write it down here. A squared minus b squared. That becomes a really cool pattern that we're gonna use. In fact, we give it a name, right? We give it a name. The name is difference of squares. In math, when we say difference, we mean subtract. So the difference between the two squares. So you got a squares, you got b squares, they subtract each other. Now, listen. We start out with this, finding this identity, looking at a plus b times a minus b equal to a squared minus b squared. Oftentimes, the way you apply this identity is you recognize that you're on this side and you get back to that side. You can have an expression look like this, and then they tell you to factor. You can factor them into this nice form. Give you an example, okay? So I'm going to give you an example on the side here. Example. Factor 9x to the 4th power minus 25y to the 6th power. Now, I give you this problem. Obviously, this is related to one of the three identities. This one looked nothing like the first two, but maybe, just maybe, look a little bit like the third one. You may think, oh, wait a minute. This is the difference of two squares, right? A squared and B squares. This one is to the 4th power, and this one's to the 6th power. How do I turn that into some sort of square? So you can think of it this way. Okay, I can see that x to the 4th power can be written as something else to the square. I can see 9 as some number square. I can see 25 as some number squares, and y to the 6th power as some expression squares. And not only that, between the squares, what's more important is this, is that there's a minus in between, right? Because our identity doesn't give us a plus, our identity gives us a minus, okay? We don't have an a squared plus b squared factor form. We don't have that. That doesn't exist. But what it does exist is that a squared minus b squared is equal to this factor form. So I can turn this, right? I can turn this into some sort of square minus some sort of square. Go ahead and fill in what's inside the parentheses. Help me come up with two things that can fit into the parentheses that will get us back to 9x4 and 25y6. Okay, so do you have 3x squared for that one? Right? Okay, good.
Oh, wait. Oh.
Yeah, you got it? Okay. Do you have 5y cubed?
Oh.
Right?
Oh, okay.
5 squared is 25. Y cubed squared is y to the 6, right?
Oh, okay.
Yeah? So keep track of them, okay? Don't loosen this. This is what being meticulous will help you. Which is actually hard for me. I'm not a very detailed person. So I do better in calculus than in arithmetics. But still, you got to overcome your weakness. All right. So now we can think of this as A, and we can think of this as B. So we end up with a squared minus b squared, right?
Yeah.
And which is a plus b times a minus b, because our identity shows us that. So go ahead and write down the answer. Use that pattern, use that formula, use that identity. So you know what A is and what B is? Show me what the final expression is. The factor expression. What is the final factor form? Do you have 3x squared plus 5y cubed times 3x squared minus 5y cubed?
Wait,
Right, because A is 3x squared, y is 5y cubed. A plus B, right? A minus B. And so look at this. You take what would have been a very hard problem to factor. You'll be like, well, how do I even start? But because of our 5-minute conversation about the identity over here, it turns out that you can use this as a tool to solve this problem. Right? Kind of go a roundabout way to go to here. So as you can see, over here, we weren't solving anything, right? We're just developing tools. And over here, we can borrow the tools that we develop and actually solve some problems. Questions on this? I'm going to introduce two more, okay? We have 3 identities down packed here. Now we're going to introduce 2 more. The next one The next one, I'm just gonna go ahead and write it out for you. I won't demonstrate or show you how it happened, but I mean, I can. Let's start with this one. A plus B times A squared minus AB plus B squared. Now, if I multiply this out, I'm just gonna do a little calculation on the side. You know, I will erase this. I will write down the actual answer here, but I'll show you how I do this, right? So A times A squared A cubed. A times negative AB is minus A squared B. A times B squared is positive AB squared. So I'm done with this one. Now I'm going to go to here. B. B times A squared is A squared B. Now notice, I still put A first, right? I still put A first. So A squared B. And then B times negative AB gives you negative, right? Because there's a minus. So negative A, and then it becomes B squared. And then lastly, we got B to the third power. Now take a look at this. I got negative A squared B right here. You had to combine like term with another A squared B. I happen to have one of the A squared B. So I have a minus A squared B with a positive A squared B. So these two terms subtract each other out. Yeah? The next one is AB squared. I have an AB squared, but over here I have a negative AB squared. So they also nicely subtract each other out. So all I am left with is A cubed plus B cubed. A cubed plus B cubed. Now, you recognize that I gave you the previous problem using the identity pattern to factor. You look at this and you say, oh, I bet the application is that if you can come up with something cubed plus something cubed, you can put them into this pattern right here. Yes? Make sense?
So it can be cube or square.
Yeah, well, this is the sum of cube. Right over here, earlier we said this was a difference of squares. This will be the sum of cubes. Now I'm going to fast forward a little bit, give you something really quick without proving it to you. But I think you can trust that I'm telling you the right thing. Okay, we have A minus B. I'm going to just put right here, minus B. And over here we have A squared plus AB plus B squared. I use blue indicate the difference between the one that we just come up with. Okay? What do you think this is going to be if you give a wild guess? Give a wild guess. That's right, A cubed minus B cubed. And this is what we call the difference of cubes. Difference of cubes. Here is an example. I ask you to factor. 27x to the 9th power minus 343 y to the 6th power. Okay, so if you look at this, you say, I need to use identity to solve this problem. Can you see?
Yeah.
Now, we know that we don't need the first one and the second one because they look nothing like the first one and second one. there's a minus in between, so I don't need the sum of q, so the fourth one also goes away. So I have a choice between using this difference of square or difference of q. I can use this one and this one to solve this problem, right? You get my logic? You get my logic? Okay. If we use the difference of square, because this is a minus, a square, you got to say, well, what is something square that gives you the x to the 9th power? Probably nothing, right? You can't really find something to do that. So I will probably also eliminate this one. So I probably say, okay, it's probably a difference of q. So I say, well, is there something to the 3rd power that gives you x to the 9? Probably, right? It seems like that's a very possible solution. So I'm trying to figure out what's in here and what's in here for my A and B. Go ahead. All right. So 3x to the 3 power. 7y to the
Second.
square, yeah, y square. Okay, so this is my A, this is my B. All right, now I'm going to write down here just because I have more room, right? So we know this is AQ minus BQ. Follow the identity right here, right? Right here. We got A minus B times A squared plus AB plus B squared. Since A is equal to 3x cubed, B is 7y squared. A is 3x cubed parentheses squared. You gotta make sure you parentheses, right? Because sometimes you forget to square the 3. Now A is 3x cubed. B is 7y squared plus 7y squared parentheses squared parentheses. Okay? Focus, focus, focus. So simplify. The first one really just nothing change over here. Over here, we gotta change that a little bit. So this is 9x to the 6th power. And then over here, 3 times 7 is 21. X cubed, y squared, plus 49, y to the 4th power, parentheses. Voila! There's a factor term, right? That is a factor of that complicated problem. So now you know how to factor this. This is a full factor. It's nice and pretty, right? Isn't it so elegant? You finish this, you like, I feel a sense of accomplishment.
No, it looks like a baby that's made in the lab.
A baby making the lab. All right.
Oh, now I know why I couldn't keep up with those because I was writing everything you wrote down.
Now, I'm going to come over here and erase this modern abstract parts. What is this?
Donate it to the museum and you get $1 million off your taxes. Yeah. Jeff!
No, Gilbert. Gilbert.
All right, let's erase this.
Exactly. It is gone forever. If you donated it to the museum, you could have gotten like $1 million off your taxes.
Whoa!
Oh boy.
Yay!
All right, you ready? You ready? You ready?
No. Why no? What do you? I thought I was done with the one.
Binomial term.
No, we're done with the
We need a fresh page for this one.
This is why we left the other.
Now, binomial means two terms, right? By two terms, A and B, right? Separated by a plus or minus, it doesn't matter. In this case, we use plus, just to make it simple. All right, so let me ask you, A plus B to the 0 power is what?
1.
Yeah, 1. Everything to the 0 power is 1, right? Who knows how they come about? Who knows why something to the 0 power is really 1?
Because you're a number. Because there's nothing to multiply together or do anything with. You have, that's just how it works. You essentially don't have a 7 in this case.
Okay, so I'm gonna give you a side discussion on that, so you don't need to write it down because it can mess up on your notes. But here's how it works, right? So if I had 2 to the square times 2 to the 3rd power, this is equal to 2 times 2, right? Times 2 times 2 times 2. And this is equal to 2 times 2 to the 5th power, right? And this 5th power, it turns out, can just be taking this one, and 2 plus 3 gives you 5. Right? Because you're multiplying. And multiplying two numbers with the same base, we call it the base, but exponents are different, and you're multiplying, you can add the exponent. This rule, you have to know where this rule comes from, you know, to use it correctly. Okay? You know how to use it correctly. When it comes with the when it goes with exponent, when everything comes with the exponent, it's a little tricky. Okay? So it makes sense when you multiply of the same base, you do that. Okay. Well, what if you have 2 to the 3rd power divided by 2 squared? This, in many ways, can be written as 2 times 2 times 2 divided by 2 times 2, right? And that just be 2 to the 1 power. So in many ways, if you have a dividing like this, you can think of it as 3 minus 2 to get to your 1. Right? So think of it this way. When you have 2 to the 3rd power divided by 2 to the 3rd power, you get 2 times 2 times 2, 2 times 2 times 2 gives you 1. But it's actually 2 to the 0 power because if we follow this pattern, this has to be 3 minus 3. So you end up with 2 to the 0 power because you are subtracting the exponent. But we do know that based on this, you agree that it's equal to 1, right? And so anything to the 0 power exponent means that it's already dividing it of itself. That's a side conversation because I'm assuming that you have learned a little bit of that last year in Algebra 1. No, you didn't? Okay, if you didn't,
Last year was supposed to be done.
oh, it doesn't matter. You learned this in Algebra 1.
Wow,
That was 2 years ago.
Okay, well then now you learned it. Okay, so end the discussion on that. We move on. Now, obviously, if we have a plus b to the 1 power, we got a plus b. Not a problem. We have a plus b squared. Let me give myself a little bit of space. A plus b squared equal to That one, right?
Yes.
I think so.
So I can say this is a plus is equal to a squared plus 2ab plus b squared. Now, a plus b to the third power. A plus b to the third power. This is what you do. I'm working out on the side, okay? A plus b to the third power is equal to a plus b times a plus b squared, isn't it?
Yeah.
A plus b is still there, but hey, a plus b squared we just figured out previously. So I'm going to put this right here: a squared plus 2ab plus b squared. So far, so good? You follow? All right, I'm going to go fast now, okay? So I'm going to multiply it out. A times a squared is a cubed. A times 2ab is 2 plus 2a squared b. A times b squared is ab squared. Plus b times a squared is a squared b. B times 2ab is 2ab squared. And lastly, plus b to the third power. So far, so good? I'm going to combine like terms. I got a cubed. This is 2a squared b. I got another a squared b. So I end up with 3 of those. 3a squared b. Okay? I got ab squared. I got 2ab squared. So I had 3ab squared. And lastly, we had b cubed. So I'm going to use that, and I put the result down here. A cubed plus 3a squared b plus 3ab squared plus b cubed. So far, so good? Okay, next one. A plus b to the fourth power. Well, a plus b to the fourth power is equal to a plus b to the fourth power is equal to a plus b times this one, right? A cubed plus 3a squared b plus 3ab squared plus b cubed.
Send it to us. My phone is red.
You can take a full photo of it in a
By the
moment.
time we end this class, all our phones are beautiful. Oh, yeah. If we go to 5, it's just.
We're gonna go to 6 and 10.
Uh-oh.
What?
What have you done? What have you done?
Okay, now ready? Ready? All right. A to the fourth power. 3a cubed b.
Huh?
3a squared b squared.
What?
ab cubed. That's just from A, right? That's just from A.
Wait a second. I thought it was from B.
No, go from B. No, let's go from B. Plus a cubed b plus 3a squared b squared plus 3ab third power plus b to the fourth power.
You promise this isn't going to be on the test, right?
Oh, it's easy. This is easy stuff. Okay?
Please.
It's gonna get easier. Alright, ready? Okay. A to the fourth power. Alright, so now we have 3a cubed b. I find another a cubed b right here. So I have 4 of those. 4a cubed b. Okay, now we have 2a squared b squared. No, I have 3a squared b squared, and I got another 3a squared b squared. So I have total of 6a squared b squared. Okay, and then we have ab cubed. Oh gosh, there's so many pens. ab cubed. I have 3ab cubed. So I got 4ab cubed, and what I left is a b to the fourth power. All right, I get to write it down here. A to the 4 power. 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4 power.
I'm not even gonna bother writing this down.
You want to do the fifth one?
No. Yes.
I don't think there's enough space.
It's just a pattern, just like
You see the pattern?
Yeah.
We'll just
Look,
all I'm saying is
Yeah.
that
What do you say?
from the first one to the last one, you just keep on adding a plus b.
No,
And you
really?
have to keep on putting the a plus b in.
Oh, wait. All right. All of you stand up. All of you stand up and come around here. Come around here. Come around here. Come around here. Circle around here.
Now you're making us.
I'm making you stand up.
You're not even.
Come on. I really want you to see this.
Do the fifth.
Hey, Malachi, come on.
Yes, you did. You're like, let's do the
Come on.
fifth, guys. Let's do the fifth. What are you yapping about?
I'm starting to see a pattern.
There's equal to
Put that on the power 0.
Does this equal the negative 1 and then go to imaginary numbers?
Yeah.
That makes it worse.
I want you to know there's a few patterns, okay?
Pascal's.
Oh, yeah, we can do that. But that's not the first thing. Oh, yeah, you can look at that too. Now, do you notice the way A and B, the way they change? How do they change? Okay, who can kind of give a wild guess?
They become more and more.
Yeah, go ahead.
The powers increase.
So the B power increase, right?
Yeah, and the A1.
So this is A1 and B1,
Yeah.
but then you can think of this as B0 and then A0, right?
Yeah.
So over here, this one, A's go from 2 to A to the 1 power to A to the 0 power. And then over here, there's no B, that just means B to the 0 power. But then over here becomes B to the 1 power, B to the B squared. Over here, same thing. A cubed, A squared, A to the 1 power, and no A. Right? And then no B, B1, B squared, B cubed. Same thing over here, right? 4, A to the 4, A to the 3rd, A squared. Does that make sense?
Yes.
That's number one observation. Hey, number one observation. Number two observation, you can check whether you're on the right track, is this. Is that the exponent of the A and the exponent of the B needs to add up to the same exponent as what you start out with. Right? H squared and B1, 2 and 1 gives you 3.
It's a pattern.
A1 and B2, 1 and 2 gives you 3. A only with the 3 and B has 0, so it's already 3, and this is already same thing here. A squared, B squared, 2 plus 2 equal to 4. Every single term, your exponents between all these variables need to add up to the same power as what you start out with. Yes?
Yes.
That's observation number 2. Get it? Observation number 1 is A will have a descending pattern of the power. B will have a ascending pattern of power, right? One goes down, one goes up. They switch flop, right? Do you see that? That's number 1. Number 2 is the power of each term ought to add up to the same power as what you start out with. Number 2. Number 3, what we need to figure out is the coefficients in front of it, right? You got 3 here, and 1 and 1. You got 4, 6, and 4. Look at this. If this is just 1, and if we call this 1 and 1, we have 1 and 1. This one we have 1 and 2 and 1. 1, 2, 1. Where do I get this 2 from? I add these two numbers, I get 2. So if I add these two numbers, I get 3. I got 1, 3, 3, 1. Guess what? 1, 3, 3, 1. If I keep going, 1, 4, right? 6, 4, 1. I got 1, 4, 6, 4, 1. So I know that what next is, right? The next one will be 1, 5, 10, 10, 5, 1. So now I know how to do this. I know a plus b to the 5th power is. I know it is 1, 5, 10, 10, 5, 1. And I know this is a to the 5th power. This is a to the 4th power. This is a to the 3rd power. A squared, a to the 1 power, and no a. And I have no b. I have a b to the 1 power, b squared, b to the 3rd power, b to the 4th power, and b to the 5th power. And I just add in between.
How many
There
years
is-
taking that?
This is called the Pascal's triangle.
Can you do this?
Looks like music theory.
Is this on a test?
Why does it look like music theory? I'm scared.
You can use this on a test, obviously, yeah. Okay.
Looks like music theory.
It is, yeah.
Oh my god, no!
All right, sit down. I'm going to show you another one. So we just learned the pattern. We just learned the pattern of Pascal triangle. And that Pascal triangle pattern shows up in the binomial expansion. When I say binomial expansion, means a plus b to the certain power, you expand them, and it shows up in that form, right? So we think that this is just sort of a kind of an interesting mathematical construction that happens on paper. Mathematicians somehow stumble into this. Okay, so let's take a step aside. Not step back or forward, but aside to a round of probability. So today, I'm going to toss a coin. I'm going to toss a coin. And coin gives you how many results when you toss a coin? 2, either head or tail. Is there a particular way in which you can control the outcome? No. Just a regular coin. Right, now that you're aware of. If you have one side weight a little bit more, you still get more of a probability, right? You can get more probability of getting one side more often than the other, but you don't have the guarantee, right? So probability, right? So we're talking about tossing a coin. There's really no reason. You can't say that this time you get a head, next time you're going to guarantee get a tail to make it match at 50-50%. You don't know. You just know that in the long run, after you toss about 100 times or 1,000 times, you're going to get roughly the same number for heads and the same numbers for tails. Yeah? Makes sense, right? So when you're tossing a coin, it's what we call very much of a random act, right? Random act. So today, hypothetically, we're going to toss a coin. Toss a coin, and I'm going to toss it 3 times. Actually, no, let's make it a little more interesting. How about let's toss it 4 times.
That's 4 times too many.
Right, toss it 4 times. And we typically will get a typical outcome. We get a head. Either we get a head or we get a tail, right? And what are some of the possibility tossing 4 times? What are some of the possible combination of heads and tails? We can have possibility of getting all heads. That's kind of rare, right? 4 times all heads. That's kind of rare, but it's a possibility, don't you think? Okay, so we have a possibility of getting 4 heads. We have a possibility of getting 3 heads and 1 tail. We have a possibility of getting 2 heads and 2 tails. possibility of getting one head and 3 tails, right? Yeah, well, let's figure it out, right? And then there's a possibility of getting all 4 tails, right? So we have these 5 different possible outcomes or combinations. Yeah, combinations. So let's write it out. It is possible I have head, first toss, second toss, you also get a head, 3 and 4. There's really no other outcome. There's just really one combination. This one, on the other hand, we can have head, 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 tail. So the 4th time we get a tail. But it is also possible that we get head, head, then tail, head. The 3rd time we get a tail. We also, it's possible to get head, tail, head, head. We also can get tail, head, head, head. So far, so good? You agree? Any disagreements on this? No, but that's not here. This is a 3 heads and 1 tail scenario, right? We can also have the 4 tails, right? We can have tail, 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 tail. So we'll do the easy one on that one. That one's easy, so we got it. Now we can also get the 1 head, 3 tail situation, right? So we can have head, tail, 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 or tail, head, tail, 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 head, tail, or tail, 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 head. So far, so good? All right? So Ali, we're tossing a coin 4 times, okay? Make sense? All right, now what about the 2 head, 2 tail situation? We can have head, head, tail, tail. We can have tail, tail, head, head. We can have head, tail, head, tail. We can have tail, head, tail, head. We can have head, tail, tail, head. And we can have tail, head, head, tail. Anything else? No? Okay. Now take a look at this. It is possible, since each head has a probability, but it's multiplying to each other because 4 times. So I have a probability, say, 0.5 of getting head. So but because I do it 4 times, it's 0.5 and 0.5 and 0.5 and 0.5. So I can call it a 0.5 to the 4th power, head to the 4th power. Yeah? Let me write it down a little bit lower. Head to the 4th power. Over here, I get head to the 3rd power, tail to the 1 power. Over here, we get head to the square, tail square. Over here is head, and then tail to the 3rd power, and this is tail to the 4th power. But guess what? This one happens 4 times. There's 1 here, 1 here, 1 here, 1 here. So I have a 4 here. I got 1, 2, 3, 4, 5, 6. I have 6 outcomes. Over here, 1, 2, 3, 4. I have 4 outcomes. Over here, 1 outcomes. So if I can just add them up, that's the probability of head, tail to the 4th power.
Yeah, let's a little familiar.
What does it look like?
Oh, wait. Oh, God.
Wow. You just
You see it? If you don't see it, I'll use a big screen for you. Look like this one, right? So when you're tossing a coin, which is a random act, it turns out that when you're tossing a coin and finding the probability of different outcomes, it turns out that it is a binomial extension. It's a result that you find in a very structured mathematical algebra situation, and yet it happens in life. Now you say, okay, this is just randomly passing points. I can apply this to your parents having pregnancies.
Oh.
Your parents want to have 4 kids. And you want to have a probability of figuring out what's the likelihood of all 4 kids are boys. You know what the likelihood of having 4 kids, having all boys, is 0.5 to the 4th power. Someone figure it out. What's 0.5 to the 4th power?
6.2% chance.
6.2% chance. Now, if you say, if your parents say, I need to have 1 girl, and I only want 1 girl. Until I get, I want 1 girl. What's the probability of that? But by having 4 kids. I want 4 kids, but I only want 1 girl.
So we're going to have to do 1/2 times 1/2 to the 4th power and then only 1/2.
4 times 0.5 to the 3rd power times 0.5 to 1 power, right?
What?
So you can actually use a binomial expansion to do these kind of practical calculations of what your chances are for having a sister or a brother.
Do you recommend having kids or no?
Huh?
Do you recommend like people to have kids or no?
Yeah.
That's a
I was trying to ask you like, hey, like if like a couple of be like, should I have kids? Like you maybe you might want to read it.
What is the probability of a choice?
This can turn into sex ed.
Oh my goodness. Now, I the whole I'm not gonna answer that question.
What do you mean?
Obviously, I like kids. But, hey, now what I'm just sharing with you, what you're seeing here, right? I mean, the final analysis here is, hey, focus. I'm talking. Now, the final analysis is this, is that the stuff that you're doing in algebra look very sort of academics. You say, well, what is this used for and all that. I mean, I'm not gonna oversell this to you, right? How often in your life gonna be able to use binomial expansion? I don't know. Are you gonna use binomial expansion to think about later on when you get married how many kids you want to have, right? I don't know. Maybe you do, but at least the fun part about this is that while you're studying something like this, not only do you get a joy of seeing the patterns emerging in the Pascal triangle as relates to the binomial expansion, it turns out that you also see happen in a sort of universal pattern in random chance probabilities and so on and so forth. It's pretty amazing, at least for me as a teacher, to be able to as a math student, to be able to see these things happening. And it gives you a better appreciation and train your brain and train your mind to be able to know those things.